With that, let's get right back into our program with the second lecture from Daniel Spiegel. Thanks.
Okay, thanks, Mike. First, I want to do something that I meant to do in my first lecture, was to give a few references. So I'm developing the abstract C-star algebra theory in tandem with the more concrete application to spin systems. And if you're new to the abstract C-star algebra theory, there's a very nice book called C-star Algebras and Operator Theory by Murphy, which is a nice book for the abstract C-star algebra theory. There's a very nice book by Professor Nikens for the applications to the quantum spin systems, which I believe is called Quantum Spin Systems. On infinite lattices. And then if all else fails, there is a Bible of quantum spin systems. What's it called? Operator Algebras in Quantum Statistical Mechanics. Yeah. By Bertelli and Robinson. OK. So let me continue now with my lectures. So right, we started with this table. We have states. We have observables. And we have dynamics. And in the Hilbert space formalism, these were, in the most generality, they're density operators on Hilbert space. We had our observables were self-adjoint operators on H, and the dynamics was a one-parameter family of unitaries, or generated by a Hamiltonian, which are both operators on H. And now we started filling out this table for the C-star algebraic formalism. The observables were self-adjoint elements now of a C-star algebra. And from Professor Sim's lecture, we know that the dynamics are now a one-parameter family of automorphisms of the C-star algebra. OK. And so now, in this lecture, we're going to fill in what are states in the C-star algebraic formalism. OK, we're going to take inspiration from the Hilbert space formalism. Right now, all we have is a C-star algebra. There's no Hilbert space yet. So we need a different way to talk about what is a state. OK, here we go. OK. The Olympics are going on right now. I'll let you take that thought wherever it goes. OK, so a state in the Hilbert space formalism. The key is to think about the state not as a vector or a density operator, but in terms of the expectation values of local observables in that state, or quasi-local observables. So if I have a unit vector in H, this gives me a map, which takes, OK, I want normal omega to be 1. this gives me a map now on B of H to the complex numbers, which maps A to the expectation value in the state omega. And more generally, if I had a density operator, then this would give me the map which maps A to the trace over A rho. OK. Now, what I want to observe about these, I need some abstract properties that I can generalize to the C-star algebraic framework. So these maps are linear. They map the identity to 1, because rho is assumed to be trace 1, and this unit vector is assumed to be a unit vector. And moreover, they are positive. And I'll say what that means. In other words, a map is positive if it maps positive elements of B of H to non-negative real numbers. OK, so let me remind you now what a positive element of B of H is. Just so that we fully understand this definition. So an element A in B of H is positive if the equivalent conditions are satisfied. Either I could have that it has a positive expectation values for all states, or equivalently, this means that A can be written as B star B for some B in the bounded operators on H. OK, this condition does not generalize well for an arbitrary C-star algebra, but this one does. This one doesn't because it relies on the Hilbert space. But this one is just written in terms of the algebra, the C-star algebra, B of H. So in general, for an abstract C-star algebra, we have a positive element. A is positive if A equals B star B for some B in A. OK. And a map, if B is another C-star algebra, a map phi from A to B, a linear map, is positive if it maps positive elements to positive elements. If it maps. A, and we say A is is positive. Thank you, Mike. OK. If it maps positive elements of A to positive elements of B. OK. So we can abstract these properties to an abstract C-star algebra. And this we take as our definition of what a state is. So a state on a C-star algebra is a linear map omega from A to the complex numbers such that omega of the identity is equal to 1, and omega maps positive elements to positive numbers. In other words, omega of A star A is greater than or equal to 0 for all A in the C-star algebra. OK. Yeah. Omega is allowed, you mean like take an infinite value here? No. All right. Behold, the magic of C-star algebras. Omega is positive. A linear map is positive if and only if it is bounded and its norm is equal to its value at the identity. So in particular, every state is bounded and norm 1. OK. So what this buys me, I can now do a very similar story to what I had for star homomorphisms on the quasi-local algebra. Right? I only need to define states in terms of local elements. So in other words, if for each lambda finite subset of lambda, or finite subset lambda of gamma, I have a state, omega lambda, on A lambda, such that this plays nicely with inclusions, such that whenever lambda is a subset of lambda prime, and such that whenever lambda is a subset of lambda prime, we have omega of lambda prime restricted to A lambda is omega lambda. Then there exists a unique state, omega, on the quasi-local algebra, such that omega restricted to A lambda is omega lambda for all lambda. OK. And this is just the exact same story I played with star homomorphisms. You can first construct omega on the local algebra. By this theorem, it's bounded. And so it extends by the BLT theorem or bounded linear transformation theorem to the whole quasi-local algebra. And you can show that the extension is also a state by this theorem if you choose. Very good. So let's do some examples. We can construct some very simple states in this way. OK. Thank you. So the norm of a bounded linear map is equal to the supremum, in this case over all norm 1 elements of the C-star algebra, of omega of A. So it's just like the operator norm on B of H. OK, so some examples. We can define some very trivial, very simple states in this way. So if you have this spin chain, you can think of, right, we were thinking of a state as some arrows on this spin chain. And we could define a state that has no entanglement, and all the arrows are doing their own thing in the following way. So if for each v in the lattice, we have a density matrix rho v, then we can define the tensor product of the density matrices. Then define rho lambda, which is the tensor product over v and lambda of rho v. And this gives you an omega lambda, which is the trace of a rho lambda. And these satisfy the coherence conditions I need. So then there exists a unique state omega on A such that omega of A is equal to trace a rho lambda whenever A is in lambda. I'll erase that a little bit. So a particular interesting example is if we take each rho v to be the identity matrix, normalized, then omega itself, this omega on the quasi-local algebra, acts like a trace against an identity matrix. And in particular, it has the cyclic property of the trace. So then omega of AB is omega of BA for all AB in A. And in fact, it's the unique state that has this property. So that's a useful thing if you want to do things like partial traces on this C-star algebra instead of on a Hilbert space. OK. We started with these density operators and also the unit vectors, which were a special case. And in particular, those unit vectors are called pure states. And there's a notion of pure state in this abstract C-star algebraic setting. So the first thing to notice, draw a little dividing line here. Actually, first I want some notation. So let's let S of A denote the state, the set of all states. And so we notice that S of A is a convex set. So in other words, if omega 1 and omega 2 are states, and T is an element of the unit interval 0, 1, then T omega 1 plus 1 minus T omega 2 is also a state. Why is it the unique state? So restrict it to any finite a lambda. Then you have a tracial state on a lambda. And there is only one tracial state on a finite matrix algebra. Maybe I leave that as an exercise. So you reduce it to the finite cases. OK. Right. So the state space is convex. And the pure states in the Hilbert space setting, they can be characterized as the extreme points. And that's a definition that generalizes to the C-star algebraic setting. So a state is pure if it is an extreme point, which means that it cannot be written as a non-trivial convex combination. Be written as a non-trivial convex combination of other states. So in other words, if t is in the open unit interval and omega 1 and omega 2 are states such that omega is t omega 1 plus 1 minus t omega 2, then that must imply that omega is equal to omega 1 and that's equal to omega 2. So that's what it means. You can't write it as a non-trivial convex combination. OK, in this example, if each of the single site states is pure, then the whole thing is pure. So sure, yeah, because it'd be multiplied by 0. Yeah, that's why I took the open interval here. OK, if each rho v is pure, then omega is pure in the example below, in previous example. OK, so that's one extremely simple way of generating pure states. How can we get more interesting pure states? Or more interesting states at all? Well, here's a little proposition, which is very easy to check. If I have a star homomorphism and a state on B, and I want this to be a unital star homomorphism, so I want them to map the unit to the unit. I'll write that down here. Then I get a new state by precomposing with alpha. So for example, one thing that is often interesting to look at is to take a product state like this and compose it with some finite depth quantum circuit. That'll give you something interesting, maybe. What about purity? How does this construction work with purity? If alpha is surjective, so in particular if it's an automorphism, but if alpha is surjective and omega is pure, then I recover a pure state. OK. So we have by now successfully filled out that whole table. We have dictionaries for states, observables, and dynamics in both the Hilbert space formalism and the C-star algebra formalism. And there's, in fact, now a way to go between them. I sort of banished Hilbert spaces, but now I'm bringing them back. They're not going to be some infinite tensor product of Hilbert spaces. They will have concrete meaning. So let's see how this works. This is through a representation. A representation of a C-star algebra A is just a star homomorphism. A star homomorphism pi now from A to B of H for some H. And let me introduce a little bit more vocabulary. So a representation is cyclic if there exists a state in the Hilbert space such that when I act with all the operators in A on omega, I get a dense subspace. So this is my notation for the set of all states of the form pi A omega. So it's cyclic if this is dense in H, meaning its closure is all of H. And a representation is irreducible if the only enclosed invariant subspaces, are the trivial space 0 and the whole space H. So in other words, if pi of A acting on some subspace X is a subset of X, then this implies that X is either 0 or the whole space. OK, that's the definition. Now let me tell you that these things exist, and exist in a very nice way. So given a state, we can define a representation. We can actually construct a representation from that state. And this is called the Gelfand-Naimark-Siegel representation, or Gelfand-Naimark-Siegel construction, usually abbreviated to GNS. OK. If omega is a state on A, there exists a representation pi, and I want to say a cyclic representation with cyclic unit vector omega such that I recover the Hilbert space notion of state through this representation, such that omega of A is equal to expectation values with capital omega for all A in the C-star algebra. OK, so this representation is not only taking me from states in the C-star algebraic formalism to observables in the Hilbert space formalism, it also takes me from states in the C-star algebra formalism to states in the Hilbert space formalism. And there's a uniqueness clause This GNS representation is essentially unique. This is very important. So if pi tilde is another rep with cyclic unit vector, tilde omega, and it also satisfies this property that the capital omega represents the little omega. Then these representations are unitarily equivalent for all A and A. Then there exists actually a unique unitary U from H to H tilde such that it maps between the two cyclic vectors. Uh-oh. Where am I going to write this? Maybe you'll forgive me if I write it here. And U pi of A is equal to pi tilde A U for all A in A. OK, I apologize for the sloppy board work. OK. So there's an essentially unique way of passing from this GNS or from this C-star algebra formalism to the Hilbert space formalism given a state. The states in the Hilbert space sense in the GNS Hilbert space H are obtained by acting on my state omega with quasi-local operators. That gets me a dense subset of this Hilbert space. So you should think of, or it's pretty good intuition to think of H here as being the set of all states that can be obtained from your original state by the action of local operators. That certainly does not include all the possible states that you could imagine. So this H here is a subset of the states that we would be interested in. OK. What about pure states? Yep.
What's the physical meaning of the cyclic vector?
The cyclic vector is just representing your state. So the state has some physical meaning. It's expectation values of A. Omega of A is the expectation value of A in that state. And this is just, it really represents the same thing. Yeah, physically. OK. Yep.
Two cyclic representations that have a same vector
Yes. Yeah.
comment on that. I don't know if this is quite correct, but I think if you take your
Sure. So the statement was just if you have two cyclic representations and they both have the same cyclic vector, then are they equivalent? And the answer is no. Oh. OK. Sure, yeah. I'm happy with that. But I think all the information that's contained in the state on the C-star algebra is pretty much contained in, I think it's pretty much the same information. OK, maybe I should stop making non-rigorous remarks. OK. I didn't want a definition. I wanted a theorem.
Is there a way to like connect this with dynamical systems?
Well, there will be a lot of connections, but how do you want to connect it? Maybe a little bit. OK. Yeah, I would guess I'd say wait till my third lecture. OK. OK. So what about pure states and irreducible representations? We haven't said anything about that yet, but maybe you can guess what's going to happen. So if omega is pure, or I guess, let me write it differently. Omega is pure if and only if its GNS representation is irreducible. And there's another important result which I'll tell you about that can also detect irreducibility. So a rep pi. A representation is irreducible if and only if its commutant is 0. So this is denoted pi of a prime. Let me write it lower so I can define it. If and only if pi of a prime. This is the set of all operators in B of h that commute with all pi of a. So it's irreducible if and only if this is multiples of the identity. So this is like a Schur's lemma for representations of C-star algebras. Yeah.
Given a pure state, how do you generate this? How do you find the
Yeah, it's a constructive thing. That's a good question. So maybe I'll try and detail that quickly. Yeah, the question was, is this a constructive? So given omega, can you tell me explicitly what h is? Sorry, what? Oh, the commutant. Maybe I don't need that parentheses. Okay. OK, so the question was how to construct this Hilbert space. The first thing to do is to look at all the operators that annihilate the state. Right? This GNS Hilbert space is this space of states that you get by acting with local operators. But if you kill the state completely, then that doesn't really get us a new state. So the first thing to do is to look at this set. Let me call it N. This is the set of A in the C-star algebra such that omega of A star A is equal to 0. And if you know where this is going, and you plug in A star A here, that means that the norm of pi of A omega is 0. So this is the set of operators that annihilate the state. And then the Hilbert space, well, you look at the C-star algebra mod this subspace, and it has an inner product. Which is, OK, I take an equivalence class here of operators. And I look at omega of A star B. You can show that this is well defined in an inner product. And then the Hilbert space is just the completion. Oh, I put a little subscript omega here. OK. So yeah, you can do this very explicitly. And you can define the representation explicitly too. OK. So what I want to emphasize is that pure states and irreducible representations are extremely nice objects. Life is good when you're working with pure states and irreducible representations. And there's so much magic of C-star algebras that happens here. And I'll share with you one of my absolute favorite theorems. This is the Catazin transitivity theorem. So if you have an irreducible representation, and you have unit vectors, or sorry, not unit vectors, but just linearly independent vectors, we'll call them omega 1 up to omega n. These are linearly independent vectors in H. If these are linearly independent. And you have an operator, T, in the bounded operators on the Hilbert space, then there exists an element, there exists A in the C-star algebra that mimics T on these elements. Then there exists A and A such that, and actually the norm of A is bounded by the norm of T. And pi of A omega I is equal to T omega I for all I. And if this T is self-adjoint, positive, or unitary, then you can choose A to be self-adjoint, positive, or unitary. So why is this interesting? Well, in general, the GNS Hilbert space is supposed to be the space of states that I get by acting on omega with local operators. But in general, that actually only gets me a dense subspace of H. But when the representation is irreducible, then it actually is the whole space. So you get everything by acting on acting on omega with local operators. So corollary is that pi a of omega is equal to H. Not, I don't need to take a closure there. Oh, yes, thank you, of course. OK. Oh, I don't think I want to erase that yet. Let me erase the top. Yeah. Uh-huh. Spanned by what?
Spanned by normalized. Like if I ask
Oh.
an arbitrary local operator,
Right, that's OK. Yeah, I guess I'm being a little loose about that. You can always normalize your state if you want. The Hilbert space contains non-normalized states and normalized states. And so by acting with local or quasi-local operators, yes, I in general get something non-normalized. But that's OK. Yeah, Robert. Good, because there is an element in the Hilbert space that maps you from omega to any other element in the Hilbert space. And you can mimic that action with something in A. Yeah. Yeah. No, I don't need irreducibility for this. The uniqueness, if you look at what the unitary does, I mean, I could stick omega on the side of this, and basically I've determined what U is on a dense subset. Yeah. Okay. Yeah. Are Hilbert spaces special? Well, Hilbert spaces are very special, but how does this theorem?
I mean, you probably have a good correspondence with those protections that I feel pretty well.
Yes. I'm not super sure how to answer your question, but yeah, OK. Sorry. OK. So I have a couple minutes left. The last thing I want to highlight is this unitary equivalence. So we had unitary equivalence of representations coming up here. And any element of, so for any, let's say we have a state in a GNS representation, so let omega in the state space of A or be pure. And let h pi omega be its GNS rep. So the Canizin transitivity theorem can tell me that if psi is another unit vector, there exists a unitary in the C-star algebra such that pi u omega equals psi. So psi also represents a state, which I'll call little psi. It also represents a state in this fashion. Is a pure state, actually. And if I keep going with this unitary, if I plug in this relation, what I get is omega pi u star a u omega, and that's omega of u star a u. So in a situation like this, we say the two states are unitarily equivalent. So we say psi and omega are unitarily equivalent. If there exists a unitary u in A such that psi of A is equal to omega of u star AU. And so we see that any two states in the GNS rep of a given state are unitarily equivalent. And we should think of these as being close to each other outside of the support of U. Right? U acts in some quasi-local region. And outside of that region, I'm acting with the identity. So omega is kind of similar to psi outside of the support of U. And I can make that precise. Right? Everything I've said for the past 20 minutes has been very abstract, all in an arbitrary C-star algebra. But if we go back to the quasi-local algebra, then there's a very nice description of unitary equivalence. And I'll end there. So let omega and psi be pure states on the quasi-local algebra. Omega and psi are unitarily equivalent if and only if, for every epsilon, there exists a finite subset, lambda, such that outside that finite subset, these states are extremely close to each other, or epsilon close to each other. So omega of A minus psi of A is less than epsilon times the norm of A for all A supported outside lambda. Sometimes you can say, or you can think of this as saying that the states are equal at infinity. And this is an example. I promised you at the start of my lecture 1 that there are phenomena that happen for infinite lattices that do not happen on any finite system size. And this is one of them. For a finite system size, all pure states are unitarily equivalent. For an infinite system, that need not be the case. Two states can be not unitarily equivalent. And whether they're unitarily equivalent or not is telling you how close they are, or that they are close outside some small local subset. And that's kind of a notion that makes sense for finite system sizes too. You want your states to be close outside some finite system, or finite subset of the lattice. OK, so I'm overdrawn 3 minutes, so I'll stop there.
Questions?
Sorry, I just got a bit confused. So psi is living in the Hilbert space in this psi and h in the second sentence.
Yep.
It's in the Hilbert space, but you're evaluating as a different psi? Oh, you're defining this
Right,
different
I have
psi.
a capital psi and a lowercase psi.
Okay, sorry.
Sorry.
That was what it was.
Another question up there.
I'm used to the definition that two states are equivalent if their corresponding representations are equivalent, GNS representations are equivalent. How do you contrast that definition with what you wrote on the
They're
top left?
equivalent. They're the same.
The same? Okay.
Yeah.
Cool. And
Um,
that's due to Cardassian transitivity?
Yeah, that could be one way to see it.
Okay,
Definitely.
thanks.
All right, one last question, then we should go to a brief break. Making me work here.
It's the Olympics, Mike.
True, yeah. All different kinds of sports represented in one lecture.
All right, so you said at the beginning of the lecture that there's a unique tracial state,
Yeah.
right, on the quasi-local algebra. So,
Yeah.
so that kind of makes me want to ask, okay, is there some kind of like 2-1 factor structure in play here?
Yeah. So if you take the GNS representation of that tracial state, you
Right.
take its von Neumann algebra, that's a 2-1 factor.
Oh, nice. And people studied it using von Neumann tools?
Do people study what exactly? I mean, the state?
The quasi-local algebra, I guess.
Oh, yeah,
Yeah.
definitely. There are a lot of von Neumann tools that come in.
Oh, yeah, that's
You
good to
have
know.
some state, you take its GNS representation, and you take the von Neumann algebra. There are lots of interesting things that happen when you ask what kind of von Neumann algebra is that.
And here's like the final stupid question. So if this double dual you take after the GNS on the quasi-local, right? You said that's a 2-1 factor. It's not the hyperfinite 2-1 factor, right?
It is.
It is?
Yeah.
Okay. I see.
Okay.
All right, great. I think we should probably move into the break. So first, let's thank Daniel again for a very nice second lecture. And then we'll have a short break, and we will come back here at 3 o'clock for the next lecture.